Hey, Matt.
Hi.
Um, do you think we should wait a minute for Ashworth, or should I just get started?
Yeah, no, we were both coming from a from us tutoring small kids to you tutoring small kids.
Sometimes I feel like I just have more experience with this kind of stuff. But
Like in relativity.
yeah, in relativity. We're gonna do some fun stuff. So I guess while we're waiting for Ashworth, let me just lay out my plan. Oh, there he is.
Oh, speaking of, I guess like a plan, I um going to the next few sessions maybe a little bit problematic just because of like AP tests, finals, and like massive projects coming up.
Mm-hmm.
I might not be able to make it to next week's classes, and then also potentially Wednesdays.
Ashworth is next week and Wednesdays in the future going to be a problem for you as well?
Oh no, not Wednesdays in the future, just like this Wednesday.
Okay. Okay, so let's just keep in mind we have 3 classes we need to make up. But Hickman said
Oh,
he
I'm
doesn't
sorry.
care if we no. I mean, it's totally fine. Hickman said he doesn't care if we postpone classes just so that we do 24 classes total.
Okay.
Okay. All right. Well, then I will continue to conduct class next week if Ashes will be there.
Could you send me videos?
Yeah, of course. I still need to do that for the previous lessons. I'll look into see which ones I've already sent.
Okay.
Um, but we still should review anyway some of the things that we're going to do. Wait, let me talk about my plan. So I want to do 2 more examples of differentiating under the integral as just an as examples of the power of this technique. Then I wanted to wrap up all of the things we've done with integration by parts and just give you like a top level view of what we've talked about. Then I would really like to uh yeah, I understand that you guys have AP classes and projects, so I can be as flexible. Oh, thank you for the cut. You're only the second person to say something nice about it today. Uh I would so integration by parts, and then after that I would like to return to the chapter on trig identities. Let's see if we can just bash those out. Because after that, I would like to focus on 3 topics. Integration involving trigonometric functions. That's deeper than just the integration by parts stuff that we've been doing. Integration of rational functions. And then I would really like to focus on Taylor series. Um, and there's 2 things about Taylor series that I want to focus on. I want to take a specifically real analysis perspective of Taylor series. Why do they work? And I want to take a combinatorial perspective of Taylor series and why they work. And both methods are worth your time to learn why. The combinatorial method shows you like where they come from, I guess, and the real analysis method shows you why they make good approximations for engineers. We're not engineers, but mathematicians care about convergence anyway. Um, that seems weird to me. Like this is just a brief digression, and then I'll go into you know actually doing some examples of stuff. But I feel like if mathematics was purely just a formal system for manipulating symbols, then mathematicians wouldn't care about supposed like paradoxes or irregularities like the statement that 1 plus 2 plus 3 plus 4 forever is equal to -1/12. And so that's one thing that kind of confuses me when someone says mathematics is a formal system and then in the same breath says we need to care about whether or not a sequence converges. Absolutely. um like there seems to be some sort of philosophical disconnect there. um but maybe I need to say more to qualify that statement more, and I don't want to waste our time talking about philosophy. So let me just remind you that last time we were trying to compute this integral without using polar coordinates, which involves doing a change of coordinates from Cartesian coordinates to regular coordinates. Let's see. Will you have the class postponed or on time next week? I guess I'll do it postponed. So that'll bring us up to 5 sessions that we have to do to make up. I'll send an email to Hikmet just explaining the situation. You see Google? How about that? Very pog Steam tag. Yeah. What was I looking up on Steam? Oh, a mod pack. Okay. Um, so last time we were looking at ways to compute this Gaussian integral without using polar coordinates. Because there is some evidence to suggest that the polar coordinates approach to computing the Gaussian integral is, or the Gaussian integral is basically the only integral that the polar coordinates approach even works on to begin with. So it's kind of like a very isolated strategy, whereas integrating under the, differentiating under the integral sign is a much more general and powerful strategy that's less appreciated. So last time we computed this by coming up with this function f of t, which we defined as an integral, which was basically just perfectly designed to cancel out into the Gaussian integral after we differentiated it. Gaussian integral plus some extra stuff. But using this method, we still computed the square of the Gaussian integral first, and then took the square root of that to get this formula right here. So then we did a digression about integrating rational functions. I'm just going to skip that because that deserves its own section. Then we did special tricks for integrating secant and cosecant, which just sort of involves being very clever with knowledge about their derivatives. So let's start today on something called higher moments of the Gaussian. Okay, so an integral of the form x to the n f of x dx for n equals to 1 to ... is called a moment of f of x. Okay, so for instance, if we, well, so how are we going to, so then this expression is a moment of the Gaussian function. And we're also going to be able to use the stuff that we do here to, again, find a way of computing the factorial of 1/2. So if we, so for, we want to do it from 0 to infinity. So for t greater than 0, we can send x to the square root of t times x, and we can get a new integral. That, sorry, that means that, whoop, see if my pen will work. Dx goes to, I might actually take a second to replace the tip in this pen because I keep charging it and yet it keeps being jerky, but I forgot where the spare tips are. I guess I won't worry about it right now. Square root of t dx. So our integral becomes 0 to infinity x to the n e to the minus x squared over 2. Whoop. Let me rewrite that. E to the minus tx. Come on. Sorry, guys. I wish I had better software available to me, but Hikmet insists I use this one. Still wrote it wrong, though. It's literally just not going to work, huh? Let's see. All right, maybe if I just keep this thing plugged in, even though I charged it literally this morning in preparation for this. Let's see if that helps. No, don't do that. Please, I'm begging you. Let's scroll down here. Let's scroll in more. Okay, so x over 2 dx is going to be equal to, I actually started with the wrong integral. All right, you know what? I'm just going to start a new page because I think it might also be that this page is just too long. Blank page after current. All right, let's try this. All right, so before we were able to compute this integral, square root of, oh, sorry, wrong bounds. Let's make that minus infinity. So this becomes 2 pi. And so if we have t greater than 0 and we send x to square root of tx, that sends dx to square root of t times x. And so we get the integral from minus infinity to infinity of e to the minus. All right, I'm gonna try using OneNote because this is just too frustrating. Let's see. View navigation page, show all, hide all. All right, moments of the Gaussian. All right, so we start with this integral, which we've already computed. And we make the substitution for t greater than 0, x going to t square root of t times x. So dx goes to the square root of t times dx. And our integral becomes the integral from 0, not 0, to from minus infinity to infinity of e to the minus tx squared over 2 square root of t dx equals square root of 2 pi. So we can divide both sides by square root of t since it is technically constant with respect to x. Dx is equal to the square root of 2 pi divided by the square root of t. So now let's do our trick of differentiating in the integral. So dt of everything. So then we get Zoom, go away. Oh, it's a chat. Let's see. Okay, you're back. All right. So we get the integral from minus infinity to infinity of minus x squared over 2, because we're taking the t derivative, e to the minus tx squared over 2 dx is equal to the square root of 2 pi over square root of t. And so we're going to get minus infinity. Oh, sorry, I didn't take the derivative correctly here. So what's the derivative of 1 over the square root of t? That should be a 2 times the square root of t cubed on the denominator with a minus sign. So then the minus signs will cancel out. So we get the integral from minus infinity to infinity of x squared e to the tx squared over 2 dx is equal to the square root of 2 pi divided by the square root of t cubed. Okay, so we can do this trick again if we just take the derivative with respect to t. And you might notice that this is only going to work for even powers of x, but we'll get to odd powers of x in a second. So if we do the derivative again, then we're going to have minus x to the fourth over 2 e to the minus t x squared over 2 dx is being equal to minus the square root of 2 pi over, there's got to be a 3 up here and a 2 down here and a t to the fifth right here. So we can rewrite this as the integral from minus infinity to infinity, x to the fourth, e to the minus tx squared over 2 dx equals 3 times the square root of 2 pi over square root of t to the fifth. Let's do this one more time, and then we'll just state the general pattern for the nth derivative. T, so then we get integral from minus infinity to infinity of minus x to the sixth over 2 e to the minus t x squared over 2 dx is equal to 3 times 5 with a minus sign square root of 2 pi over 2 square root t to the seventh. And so we can clear the minus 2's from both sides, minus 1/2, I should say. Get x to the sixth e to the minus t x squared over 2 dx is equal to 3 times 5 square root of 2 pi over t to the seventh. So, after doing a few examples of this, then we can infer, and we could prove it by induction. I don't really feel like doing a proof by induction. Let's just infer it, that the nth derivative of this is equal to x to the 2n e to the minus t x squared over 2 dx is equal to, let's see what the chat says. There isn't a square root. You got it. All right, let's put that 2 right there. So that's going to be is this the best way of stating it? Now I can see why the author wrote it this way. All right, this is just going to be a cleaner way of writing it. Let's see. No, we'll be fine. We'll be fine. We can do it this way. d dt n integral from minus infinity to infinity x to the 2n e to the minus of this, I should say, is of e to the minus t x squared over 2 dx is equal to the integral from minus infinity to infinity of x to the 2n. No. Okay, all right. I don't want to mix up our logical things, so I'll state it this way. d dt of n to the n of this equation 2 pi over square root of t gives us this new equation that the integral from minus infinity to infinity of x to the 2n e to the minus t x squared over 2 dx is equal to 1 times 3 times 5 times ... all the way up to 2n minus 1 square root of 2 pi over t, the square root of t to the 2n plus 1. That looks right to me. So this is all the even powers. If we just set t equal to 1, then we get the even moments of the Gaussian are written this way. Times 3. Oh, there's no, the t's go away. So we just have 1 times 3 times 5 times ... all the way up to 2n minus 1 times the square root of 2 pi. All right, that's not so bad. What about the odd powers? So let's look at minus infinity to infinity, x to the 2n plus 1 e to the minus x squared over 2 dx. So I claim that this is actually 0. Can someone tell me why it's 0? There's a really easy way to state why it's 0. So that is an even function, and that is an odd function, and the integral from minus b to b of an odd function is equal to 0. So the area on the positive side of the x-axis has the opposite sign to the area on the negative side of the x-axis, but otherwise those two areas are the same. So we don't have to worry about the odd powers because they're all equal to 0 anyway. So how can we use this to compute 1/2 factorial again? Well, so what we're going to do is, according to the gamma function, this would be the integral from 0 to infinity of x to the 1/2 e to the minus x dx. Can I get someone to try to guess a substitution to turn this into a moment of the Gaussian function? Yeah, I'm going to use a u though. So we would say that u squared is equal to x. So du 2u is equal to dx. And so this integral becomes the integral from 0 to infinity of, that's going to be u e to the minus u squared d times 2 u du. So it's equal to the integral from 0 to infinity twice that of u squared e to the minus u squared du. But we want this to be from minus infinity to infinity. So fortunately for us, this is an even function, which means that it's symmetric about the y-axis. And so we can divide it by 2 if we just flip the bound over to the other side. U squared e to the minus u squared du. And here's where I want to do another substitution. So we can say v is equal to u over the square root of 2. Or let's do it that way. V is equal to u over the square root of 2. So dv is equal to du over root 2. So then this integral is equal from minus infinity to infinity of v squared over 2 e to the minus u squared, or sorry, v squared dv over root 2. And so we could rewrite this as 1 over 2 root 2 integral from minus infinity to infinity of v squared times e to the minus u squared over 2 du. But we know from this formula that if we set n equal to 1, that this is equal to 1 over 2 root 2 times root 2 pi. So we get square root of pi over 2. So yeah, differentiating under the integral sign is very powerful for computing moments of the Gaussian, computing the gamma function. There's a famous, how should I say this, like anecdote that Richard Feynman, a famous physicist who invented a lot of stuff regarding integrals, when he was like an undergraduate at Stanford or something like that, he was able to solve a lot of previously unsolvable problems because of this trick that he employed. So now let's look at another example, a final example of differentiating under the integral sign. Well, let's see if I, oh, that one's a good one. The problem with these is the deeper that this paper goes, the more you have to know things about real analysis that I would really prefer just to wave my hand over. But it makes it hard to explain the why some of the things are true. So should we do this one? Let me just double check to make sure. I plan on doing this one. Just let me double check. Okay, this one shouldn't have too much hand waving. So let's define f of t to be this integral 0 to infinity of cosine of tx times e to the minus x squared over 2 dx. So this is a cosine transform of the Gaussian. And typically in math, actually, a transform is basically using an integral to turn a function of x into a function of t. And these are very important in solving differential equations. I have no idea where this one came from, but you know, it's the paper put it in there, and this guy, Keith Conrad, is a really good author for undergraduate math. So he thought it was worth our time. So I'm going to agree with him. If we take the t derivative of this thing, then we're going to get a minus t times the integral from 0 to infinity of sine of tx e to the minus x squared over 2 dx equals, sorry. And have we done integration by parts for things like this? Well, I actually already did it wrong. This should be an x. So let's rewrite this as minus t times the integral from 0 to infinity of sine tx x e to the minus x squared over 2 dx. So yeah, let's do some integration by parts. I don't want to spoil it. I don't want to spoil it just yet. Someone try to figure out what the substitutions that we want to make for integration by parts are.
Would one of them be sine tx, and then the other one would be negative x squared over 2.
That would leave these behind, right? So our two pieces for integration by parts have to cover the whole integrand. Like we want to find a u and a dv, right?
Yeah, but doesn't the negative x squared over 2 kind of cover the x by turning it into a dv? Deriving it, you get negative x, and then you can.
Well, then we would be left with this thing, right?
Yeah. So you could simplify it out and get like a derivative. Like if u was negative x squared over 2.
Let's try it. The derivative covers that. Well, we're taking the derivative with respect to x here. It's good. So the x wouldn't come out when we did the chain rule. If we did dv is, that wouldn't work. We need to have.
No, I mean, if u was the exponent, and if you took the derivative of u would be negative x. So if it was du,
All right.
If you took a derivative of it, you would get du equals x negative x dx, right?
Yep.
So wouldn't that be a useful substitution?
And we could say dv is equal to sine of tx dx. I just wanted to make sure that I was hearing you correctly.
Oh, right. I forgot how substitution by parts works. You need the dx in the other one, right?
This would be over t. Yeah, right?
Yeah, I forgot about that one. Sorry about that.
This still wouldn't quite work because we would have an e there. So this is something where you just kind of have to stare at it a little bit before you realize that x e to the minus x squared over 2 is equal to the derivative with respect to x of minus e to the minus x squared minus 2 times this. Let me just make sure I'm getting that correct. No minus 2, just that. So that makes it a good candidate for setting it to our dv. So if we say u is equal to sine of tx and dv is equal to x e to the minus x squared over 2 dx, then du is equal to cosine of tx over t, times t. And v is equal to minus e to the minus x squared over 2. And so we get that our integral minus t integral from 0 to infinity of sine tx x e to the minus x squared over 2 dx is equal to minus e to the minus x squared over 2 sine of tx going evaluated at x equals 0 to x equals infinity. And then, oh, you know what? I'm just going to forget this minus t for now. We'll take whatever we get at the end and multiply it by minus t. And then we have a minus. There's a minus in this v, so that becomes a plus. The integral from 0 to infinity of e to the minus x squared over 2 times t cosine of tx dx. So this thing right here is t times our original integral, right? If I put the t on the outside, we had, Our original integral is cosine of tx e to the minus x squared over 2. Why is Mr. Keith Conrad disagreeing with me? Keith Conrad actually made this substitution. So he moved the minus sign right here, and then we made a minus here, so that becomes a plus. So this is a plus, and this is a minus. It won't affect our answer in the end. I just want to make as many or as few digressions from the source text as possible. So we have this integral now. Let's evaluate this. So at x is equal to 0, we have, sorry, at x is equal to infinity. As x goes to infinity, sine of tx just bounces up and down between 0 or 1 and minus 1, so it stays bounded. Whereas e to the minus x squared over 2 decays to 0 very incredibly rapidly. So it goes to 0. We get 0 minus, and then if we plug in 0, we get 1 here. And for sine of 0, that's 0. So we also get a 0 here. And that's kind of neat that this integral completely cancels out, or that this antiderivative is 0. And then we have minus t times our original function. So let's state what we just got as a differential equation. We took the derivative of ft, and we got minus f of t. So f primed of t is equal to minus t f of t. Does anyone know how to solve this differential equation? This is a differential equation that can be solved using calculus 1, actually.
So wait, would this be d over dt equals negative x? Or sorry, I've done these in x and y. So it'd be dx over dy equals negative xy. Oh, dy over dx. Okay.
Yeah, equals minus x y. Yep. You could think of it this way. This is what is known as a separable differential equation. I'll write it like that. Separable differential equations are basically as nice as possible. The nicest differential equations you could get. So basically you have, let me just show you the general way of solving something like this. So if you have p of x y primed is equal to q of x y, then you can rewrite this as y primed over y is equal to q of x over p of x. And then if you just integrate both sides, well, this might be a rational function, but in our case, it's just going to be a polynomial. And so we will get the ln of y is equal to this integral, whatever it is. I'm just going to leave it like this, plus c. And then we just take e to both sides. So that's the strategy. Let's solve it for our specific instance. There are other ways of solving this differential equation. It looks a lot like the differential equation for e to the x, right? E to the x's differential equation is this, with f of 0 is equal to 1. And we could solve this using series methods. For instance, one of the ways that we found e to the x, but there's no need to do so much work for this. So we have f primed of t over f of t is equal to minus t. If we take the integral of both sides, we get the natural log of the absolute value of t is f of t, sorry, is equal to minus t squared over 2 plus c. And if we take the exponential of both sides, we get f of t is equal to, we can drop the absolute value signs, and actually we didn't need them because our function is positive to begin with. That's one of those real analysis things that I'm just going to wave my hand at. And so we get c e to the minus t squared over 2. And so we need to solve for this c. So, but what we had before is 0 to infinity cosine of tx e to the minus x squared over 2 dx is equal to some constant times e to the minus x over 2. And so what is a value of x that we can use to solve this for? Oh, and that actually should be a t, not an x. That will make our lives a lot easier. So, well, we actually already know that the integral from 0 to infinity of minus x squared over 2 dx is equal to square root of 2 pi. Let me just double check real quick. There's all these 2's floating around depending on where we put it. Let's see. Go back to the previous page. Oh, we don't want to look at that. Let's say we said it should be divided by 2, square root of 2. Square root of pi over 2. So here we're setting t equal to 0. And we're going to get this integral after that. But we know that this is equal to c because we set t equal to 0 in this equation as well. So we got a 1. So then we get that the integral from 0 to infinity of cosine tx e to the minus x squared over 2 dx is equal to the square root of pi over 2 times e to the minus t squared over 2. That's pretty nice. So let me see if I want to do the next example in this paper. It has a lot to do with Gaussian integrals, this paper. Are we gonna have to use Euler's reflection formula? No. Let's save this one for next time. Let's just summarize some of the integration by parts stuff we did and solve some more interesting integrals that fall outside of. So here. Oh, why did I move that over here? We want this right here. Want my notes for this one though. So general strategies for integration by parts. Okay, so I'm going to define what are type 1 integrals. And these are going to be stuff of the form a polynomial times e to the ax plus b dx, or these two right here, polynomial times sine of ax plus b dx, or cosine. The reason that we're not going to consider other things like tan or cosh or secant is because, well, we could do cosh. This would actually work just fine with cosh and sinh, but things like tan and cotan and secant, they are not so simple to state. So for this, we would just set u equal to p of x, and dv equal to our transcendental factor times d of x. And the reason that we do this is that du is going to be a polynomial that's degree 1 less times dx. And this is just going to stay transcendental, right? But if our polynomial was just a constant, then we could integrate all of these very easily. Transcendental. Did I spell that correctly? Dental. So this is what's known as a like power reduction method. And that's one of the things that integration by parts is really good for, is just reducing the powers of your integral. So we've done tons of examples like this already. So let's state type 2. So that would be an integral like a polynomial times the natural log of ax plus b, or an integral like a polynomial times arc. And I'm just gonna, instead of writing 4 integrals, I'm just gonna say sine, cosine, tan, or cotan. Secant and sinh, sorry, yeah, secant and cosecant have their own wackiness involved with them, so that's why they're excluded with this. But if it's any integral like this, then the strategy is just to set u equal to the transcendental term. Whoa, what happened there? And dv equal to the polynomial. The reason that we want to do that is when we take the derivative of u, we're going to get a rational function in ax plus b. So then we will just be on the level of integrating rational functions after we do that, which is a lot easier in general. Okay, and then type 3. And the reason I'm not showing examples of these is because we've basically just been doing examples of these, and I want to get to integrals that fall outside of these types. So would be e to the ax times b times sine of x dx, and e to the ax plus b times cosine of x dx. And the way that we want to solve these is we want to do integration by parts twice. Twice to get a linear equation of our integral. I should say, to solve a linear equation of our integral. Solve a linear equation, I should say, for our antiderivative. So we already did this for e to the ax times cosine and sine of x dx to get a general formula. Do you guys want me to remind you how it went, or should we just go on to the beyond the 3 types integrals?
I'm going to go beyond.
Okay. All right. So let's try this integral. I'll give you guys a moment to see how you can make this work. So the natural log of x squared plus 1 dx. This one is really sneaky. This one's really sneaky. I'm just writing these preemptively. I'm not giving anything away. Oh, I forgot to show you guys the special integral from an integral B that led to one person getting absolutely humiliated. Uh, I guess we'll do it after this integral. It doesn't require integration by parts, but it's one of those integrals that you would only ever see on a contest. Because if you see the right solution, it's very trivial to solve. Did I write it down? I did. Okay, good.
We should use integration by parts, though, right? Yeah. Okay.
For this one, we should be using integration by parts. For the next integral, you could try integration by parts. Man, I wrote all these notes of things to do. I'm glad that I wrote more notes than we were able to get through with, but there's some neat formulas that we can prove with integration by parts, just in the idea of just reducing powers of certain annoying integrals. All right. In the interest of not using up all our time,
Whoa, wait. I think I got something.
okay.
I want to make sure. Arctan is x squared over x squared plus one, right?
Um,
Like that's the derivative.
the derivative of arctan is 1 plus x squared,
One plus x squared.
or 1 over 1 plus x squared.
Oh, okay.
If you had x squared over 1 plus x squared, you could just do um, it would be
Oh wait, yeah,
like
no, I think I can simplify that. I can get x squared plus one over minus arctan, right? So I would get x squared plus one minus one over x squared plus one. Yeah, and then I could get one minus one over x squared plus one. And then deriving that I get x. I'm sorry, integrating that, I get x minus arctan.
That might be a solution. So let's what did you say u and dv equal to?
Uh I mean I didn't really see any other solutions, so pardon me if I'm wrong here. But would you just be ln x squared plus one?
That's exactly what it is.
Oh, okay. That seems kind of dumb, but okay.
Yep. But
I
in
assume
this
that
case,
seems
what
like
you're
wrong.
recognizing it'd be a lot easier to integrate the derivative of this thing than it would be to So that should be like 2x squared over 1 plus x squared, right?
Wait, can I get semi-final answer? Like, I
Sorry.
want to make sure I got it right.
Okay.
X ln x squared plus 1 minus.
Oh, I don't have the solution. Here, let me see.
Oh, okay, okay.
Let me see if I can find the solution. I just know how to solve it. But
Oh, so solve it and then I can check.
okay. All right. Fair enough.
Sorry.
So if we take the derivative of this, that's going to be 1 over 1 plus x squared times, that's got to be 2x, right? By the chain rule.
Yeah.
So then v would be x. So this integral ln x squared plus 1 dx is equal to 2x squared over 1 plus x squared minus the integral of 2x dx over 1 plus x squared. So I don't think you would be getting an arctan out of this because we could just say u is equal to x squared plus 1, du is equal to 2x dx. So we would have 2x squared over 1.
Wait, don't you get did you put the right things on the outside?
Du is equal to this dx. Did I put the right things on the outside? It should be, oh no, it should be x ln x. You're right, you're right. X ln x squared plus 1. Yeah, so that should be here as well as a mistake. X ln x squared plus 1. Good catch. So we have, oh no, and this would also still be an x squared. There we go. So it would be an arctan.
You can factor out the 2, right?
Yeah. So that would be, let me just write this correctly. X ln x squared plus 1 minus 2 times the integral of x squared plus 1 minus 1 dx over 1 plus x squared. So that's going to be x ln x squared plus 1 minus 2x plus arctan of x plus c.
You need to put parentheses around it, don't you?
Well, we have a minus sign right here, right?
Yeah.
And then a minus sign right here. Oh, there should be a 2 here.
Okay, yeah, okay. Yeah, that's what I mean.
Does that look correct? So
that is what I got. Yeah.
All right. So then let's try this one. Last integral of the day. Next time we will do a couple more integrals like this. Let me give you just the challenge integral, which is extremely trivial if you see the right thing. 2x secant of x plus x squared secant of x tangent of x dx. There are a lot of ways to overthink this integral. This is something that you would see on an integration B, whereas the things that the integrals that we've been studying are honestly kind of like integrals that you would see in real life, if I had to be frank. So this is more like an integration B integral, but I'll let you try to solve this on your own time because I have to get to my next class.
Wait, before you go, can I post an image in the chat?
Sure.
Okay, wait, I want to give you a quick puzzle. I'll try to do it as quickly as possible. Yeah, sorry for wasting time.
I mean, it's all right. I'm just going to talk about computing radicals with these kids.
I see. Okay. I sent it to Partha. Okay, found it.
What grade? Math counts. So like 5th to 7th grade. We're gonna use the Babylonian method, which kind of sucks. It doesn't converge very fast. And then I'm gonna show them how to use difference of squares and continued fractions to get a method that converges much more quickly. Is a kid named Dev in your class? I don't think so.
Okay. So it says find a nice formula. Finding the nice formula is really easy, but then prove it.
Okay, so given a positive integer n, consider all the subsets 1 to n. For each subset, let consider the product of all the elements in the subset. Let Sn be the sum of such products taken over all subsets. Ooh, that looks fun.
Within a minute, you can find like the right formula, but prove it without induction.
Prove it without induction.
Yeah.
That looks like a great problem. Thank you, Matthew.
All right. Yeah. You have to get to your rest. So bye.
Later.